Hello. At this point, we now have successfully matched our lines between the model and data features, and we've estimated the rotation and translation that moves the model and aligns it with the data. Unfortunately, through a combination of the matching algorithm and the pose estimation algorithm, we may have a lot of extra solutions to this problem, estimated matches and rotations and translations, that don't really correspond to the actual object. The correct matching. They'll just have the object in some sort of funny sort of place. Well, the goal of this next stage here is the verification stage, is to eliminate a lot of these false matches. We get quite a fair number of them we would like to be able to eliminate so we can be certain that we've actually correctly matched the object. In addition, as well as correctly matching the object, we also like to estimate that we have a good pose for the object. And that's because we want to be able to have our robot come in and pick up the object or drill a hole or something like that in it. In the same way that we use the geometry of the objects in order to estimate the pose of the object, the rotation and translation, we're going to use that geometry again to help verify that we've got a good match. We're going to do this in 3 stages. The first stage is going to look at the alignment of all of the edges on the object. If the object has been perfectly matched and translated and rotated into place, then you should be able to take that model and lay it directly on top of the object in the image, so all the edges will align up, and that's what we'll see. So we're going to do this in 3 parts. We're going to check for this in 3 parts. And the first of which is the test given here, and that asks, are the model and the data lines parallel? So here you see an example of where they are more or less parallel, and we want to test, well, are they parallel enough? In this case, that looks good, but with our errors in model matching and pose estimation, we may get alignments that are not good like this. We want to test that. The way we're going to do that is we're going to create the unit vector, which goes through the model points. So that's a direction vector here through the model points and through the data points, and we're going to take the dot product of those two. And if these 2 vectors are aligned, either this direction or potentially in the opposite direction, the dot product should be either close to 1 or -1. And that's why we've got the absolute value here. So we take the dot product, and it should be close to -1, so we check to make sure that it's bigger than some threshold. Now here actually we've used a rather generous threshold of 0.9 rather than 1. And that's because we're going to use a bunch of tests. These tests will apply to every single pairing of the objects, and we've got 3 different tests. So we don't want to make the test too strict because our segmentation algorithm and our corner finding didn't get exactly a perfect description. So we have to be a little bit tolerant to allow for these small errors right here. So in this case, actually, we're going to be quite tolerant, make it very generous, but because we have so many tests that we're going to use, even though we've got a generous test, the whole collection will be successful in eliminating all of the bad matches and the bad pose estimation. Right, so here is our first test, is are the 2 lines parallel? The second test is asking, are these 2 lines close to each other? Because they should be as close as possible in this direction. So in this case, we're going to look at the distance between the lines. And so we're going to set that up algebraically. We're going to take our model vector here, and we're going to take the unit vector here, and we're going to look at the perpendicular unit vector right here. So that's described by this. That's the W right here. And then for each of these endpoints, we're going to look at the projection of this data point down onto this sort of the infinite line which goes through these right here. So that's the expression for the error at one end, and similarly we can get the error at the other end. So that gives us a value which should be 0. If everything was perfectly aligned, we would have a 0 distance between. But as I've said, we're going to have a little bit of error right here, so we need to have a tolerance on that. And in this case, again, I've used a very generous tolerance, just for all the same reasons that we talked about previously, of 15 pixels. The third test is asking whether the data lines overlap. The reason for that is the first test sort of sees, are the lines in the same direction? The second test sees, are they close together? And the third test sees whether they overlap. in this direction. So we kind of know they lie here somewhere, but now we want to see whether they actually land right on top of each other. And this is another algebraic form of test. In this case, instead of looking at the perpendicular distance along here, we look at the point where it projects onto, and we want to know the distance between the projection and the endpoint. That's this lambda distance right here. And again, we can set this up algebraically, and that's our formula right here for creating that distance at lambda. And we want that lambda to be sort of close to 0 in this particular case. And we've also set it up here a little bit so that the tolerance is a function of the actual length of the segment. Right here, so we've got the length of the segment, and we've got a tolerance. This endpoint could have been a little bit off the end of it, so that could be negative. That's why we've got the negative tolerance here. Or it could be a little bit on the other side of it. And that's the other end of the tolerance right down here. So the net result is that's the third test right there. So as I say, we put the three tests together for the direction, distance, and overlap. When we put all of those together with our examples, we can see here are some examples of the success of that. What we've got here is the original image, so that's the kind of the gray and the black, and then we've taken our model and we've drawn them on top. And this is from the successful matches where we've done the matching and then estimated the pose, the rotation and translation. And we've eliminated all of the false matches here as well too. And you can see that it's reasonably accurate. There is small gaps between the drawn lines and the edge of the object. That's partly because of I guess maybe not complete accuracy in the estimation of the scale factor. And also there's a little bit of shadows around the edges of the object when we took the images. So the real measured objects are not quite the same size as the images of those objects. One of the things we would like to do is not just examine a couple of examples, but we would like to examine a large number of examples just to see how well our algorithm performs. And so I showed you previously a set of the segmented boundaries for all of the objects. And in this case we had 12. We had 4 examples of each of the T shape, the thin L shape, and the thick L shape. This is a summary of how well we've done in a kind of representation called a confusion matrix, where we say for each of the true shapes right here, how many of them were estimated in each of these different categories. And we could say it could be in the 3 known shapes, or perhaps no matching actually took place, no correct matching of estimating the translation and the rotation and then the verification. Something went wrong. And you can see this for those 12 example images that I showed you previously. You can see this is our confusion matrix. When we first generated this, I was a little bit surprised to see that there was one incorrect match. Nothing successfully matched right there. But later when I went back and looked at the image data, I discovered actually that the part here had been flipped over when we took the other image of it. And that's why it didn't match. It no longer matched the L shape like this. It was an L shape like that. Okay, and it didn't fit the model. And that's exactly what we want. We want our model matching algorithm to reject things that don't fit the model. So what have we learned here? Well, this is quite a long sort of set of steps that we've taken. We've looked at a way of representing the objects. We've looked at a way of extracting straight lines from the boundaries of objects in images. We've looked at a matching algorithm. We've looked at a pose estimation algorithm. We've looked at a verification algorithm. All these pieces we needed to put together to be able to do our model matching of these two-dimensional flat shapes. The kinds of techniques that we've used here have been simplified purely to deal with just these polygonal shapes, but real objects generally are more complicated than that. Fortunately, a lot of the techniques we looked at here can be extended to a few other shapes and components, whatever the circular arcs, the corners, and the holes. These are typical parts of mating needed for the mating of objects, connecting them together. So they usually have these kinds of things. And we can work off that. More exotic types of curves going around the boundary of the objects are much harder to work with, and therefore we can kind of stay away from those, provided we have enough of these features that we can work with. Interestingly, we will also come to use this, pretty much the similar sorts of techniques, but extended into the 3 dimensions when we get to the stereo example. And there we will be doing again the model matching pose estimation verification, but in 3 dimensions rather than in 2 dimensions. Thank you.